So in this video, we'll look at the special case of two-dimensional range reporting. We saw in the previous video that using range trees, we can answer two-dimensional range reporting queries in nlog n space and log squared plus k query time. It turns out for a special case of two-dimensional queries, we can do much better. So this special case is known as three-sided queries. A three-sided query is shown in this picture. So such a query has only three boundaries. In other words, it can be written off as the Cartesian product of interval x1, x2 times an unbounded interval y2 plus infinity. Given such a query, we'd like to list all the points inside the query. This can be done using a data structure that is known as a priority search tree. So it is a combination of a priority tree plus a search tree, and that's why it's called a priority search tree. It is relatively simple to build. So the pseudocode to build such a priority search tree is as follows. First, you find the highest point P in your input. So this point has the highest y coordinate. Then you partition the remaining set of points in two halves based on x coordinates. So you build the point set PL that contains remaining points. So you remove P from the point set, then you cut the remaining point set in half. So something like this. And then you store V at a node that's going to be the root. You store the dividing line VD that is used to divide the points in half. So this VD could be an x coordinate that is between the smallest x coordinate of PR and the largest x coordinate of PL. And then you recurse on the left side and on the right side of this dividing line. So in other words, the highest point in PL will be the left child of V, and the highest point in PR will be the right child of V. And then the construction continues recursively. So if you want to look at this subtree, so after removing this, you cut this in half using this dividing line, and then this will be the left child and that will be the right child. So this will be the priority search tree built on the original 7 input points that we saw. Obviously, such a priority search tree uses linear space because you have exactly n nodes in such a tree. Every node, including internal node as well as the leaves, is stored an input point. And every input point is stored exactly once. So the space is O of n, or in fact exactly n nodes. Let's look at a query. So the query is relatively simple, even though it's slightly more complicated to analyze. So consider a query region, a three-sided region like this. The first easy case is if this query region is higher than the point V. If the point V, remember that the point V is the point with the highest y coordinate. So if the query interval has higher y coordinate than V, then it's obvious that nothing in the point set can be inside the query. So in this case, we basically return nothing. Otherwise, we continue with the query procedure. We first check the pointer stored at PV. If it's inside the query region, we can just output it. So we produce an output containing that point. So these two are the easy cases to handle. And then we continue with with step 3. The step 3 and step 4 are again relatively easy. If the query region is complete to the left or complete to the right of the dividing line, then we recurse on the proper subtree. If it's to the complete left, then we recurse on the left child. Otherwise, we recurse on the right child. So the interesting case is, again, similar to the range trees, when this query region intersects the dividing line. In this case, we recurse on both sides. So we recurse on the left child and also recurse on the right child. It might seem that such a recursion will lead to an inefficient algorithm, because if you write the recursive formula for the running time of this algorithm, this will be that the query time that it takes to answer a query on endpoints is going to be equal to 2 times the query time it takes to answer n over 2 points. So if you write that recursion, it will solve to linear. So that will be a very slow query. However, we can analyze the query in more details. What you need to realize is that the queries here are in fact two-sided queries on the left and another two-sided query on the right. And this will be very helpful in analyzing this algorithm. So when we call this query algorithm recursively using VL and Q, Q is in fact will be treated as a two-sided query on the left child, and Q will be treated as a two-sided query on the right child. This means we can analyze it as if we're calling a different procedure. We're calling a two-sided query on a node V. The pseudocode is exactly the same because we're actually calling the same procedure, but we're analyzing it using differently. So to answer a two-sided query, again, we have the cases 1 and 2 that were 1, 2, 3, and 4 that were relatively easy to handle. Observe that when you, in this case, step 3 cannot happen, but that's not a problem. It means that you can write a slightly more efficient code, but it will not change analysis. Again, the interesting case is step 5 when the two-sided query intersects this dividing line. In this case, you can notice that we have a two-sided query on the left plus a one-sided query on the right. So in this case, the two-sided query on the left is answered recursively, whereas the one-sided query, we can analyze it slightly differently. So how long does it take to answer a one-sided query? Well, as you can notice, a one-sided query is essentially listing all the points that have y coordinate above a certain point. Observe that a priority search tree is in fact a priority queue, where the y coordinate is a key. So finding the smallest elements in a queue can be done efficiently. In other words, finding the smallest element in a priority queue can be done in O of k time. So this means a one-sided query can actually be answered in the size of the output. So to summarize, we can write a recursion for a three-sided query as is the following. So imagine we want to answer a three-sided query on endpoints. If step 3 or 4 happen, then we spend constant time during steps 1 and 2 and 3 or 3, and then we're recursing on a problem that size has n over 2 size. So this is a recursion if step 3 or step 4 kick in. If step 5 kicks in, then we are recursing on 2 problems that have size n over 2, but we're recursing using a two-sided query. So we can write this recursion instead. What is the situation for a two-sided query? If you have a two-sided query, again, step 3 or 4 will give you that we are recursing on a two-sided query on half of the input points. And again, step 5 is the interesting case. In this case, you're recursing on a two-sided query on half the points plus a one-sided query on half the points again. So in this case, this second branch of the recursion is obviously more costly than the first branch. So for the worst case analysis, we can assume that the second branch always happens. In this case, the first branch is again cheaper than the second branch. In fact, the first branch can only lead to log n plus some recursion on an input that is smaller. So the first branch can only give you an added log n until the second branch of the recursion happens. And as we said, the recursion for a one-sided query is essentially an order of the output size. So putting all these together, we can see that both three-sided and two-sided queries solve to log n plus k. As I said, the first branch of the three-sided query can at most solve to log n plus 2 times recursion on a two-sided query. Two-sided query, the first branch is always less costly than the second branch. So the second branch solves to this recursion, and as we saw, T1 of some input points is essentially O of the output size. The sum of the output size, if the sum of all the output size is k, then This recursion solves to log n plus k, and as I said, the recursion on a three-sided query also solves to log n plus k. So in summary, using a priority search tree, we can solve three-sided queries using linear space and log n plus k time. Observe that priority search tree cannot count the number of points inside the region. It can only report, whereas range trees could either count or report the set of points inside the query range.